Hello and welcome to another tutorial. We are looking at operators, and now we're looking at the bitwise and bit shift operators. And these are the operators that basically operate on either one operand or two operands, right? So they're either unary or binary. For example, Bitwise Not operates only on one operand, and it just flips all the bits of that particular operand, right? So the Java programming language also provides operators that perform bitwise and bit shift operations on integral types. So this is the key limitation for the primitive types. And remember, these bitwise and bit shift operators only work for primitive types, and they have to be integer types like int, byte, short, int, and long. And Java doesn't provide, by default, doesn't provide operator overloading. So there is no concept of bitwise or bit shift operators for classes that you define. But we will see that with the help of your IDE, such as Eclipse IDE, you can overload these operators for your own custom classes, right? The operators discussed in this section are less commonly used. Normally the shift operators are used whenever you're dealing with colors, RGB colors, like a mask, color mask, and then you can extract only the red bits or the green bits or the blue bits, for example. We will look at an example for this later. Therefore, their coverage is brief, so they're not going to talk about these that much. The intent is to simply make you aware that these operators exist. The unary bitwise complement operator, not, we call it not operator, bitwise not. Bitwise not means it flips all the bits, inverts a bit pattern. It can, remember, integers are stored as bits. They're signed integers. All of the integers are in Java are signed integers. So if they're positive, they have their own bits. If they're negative, they are stored as 2's complement. It can be applied to any of the integral types, making every 0 a 1 and every 1 a 0. For example, a byte contains 8 bits. Applying this operator to a value whose bit pattern is all 0 would change its pattern to all 1. All 0 is positive because the leftmost bit it's the sign bit, and then it becomes 1, which means now it becomes kind of a negative number, right? So let's create a new class, bitwise operators. Let's have a main method here, and we're going to create a public static void test1 method here, and I'm going to call the test1 in the main function. Now we're going to look at the bitwise not, which means flips the bits. And how do we do that? Let's create a byte. B1 is remember, we said when we defined the literals, we said that if we want to define a binary, we start with 0 bit. This tells the compiler that we're defining a number as a binary, and then 1, 2, 3, 4, 5, 6, 7, 8, right? So obviously, if I add one more, I get a compilation error. Actually, I don't get a compilation error, but here now I get a compilation error. So if something is more than 0, for example, if I put this to 1, this works because this can be converted. This has a let's also differentiate every 4 bits. Java allows underscore in literals, right? So 4 bits, 8 bits, this is 9 bits, but it still works fine with bytes because it can be safely truncated. However, if I, for example, set this bit to 1, this doesn't work because it says that cannot convert from int to byte, because this now has more than 8 bits, and anything that has more than 8 bits, basically the default for integer numbers is int types, right? To refresh your memory, the default for integer or integral literals is int. As long as an integer can be converted implicitly to byte, which means it fits a byte, then the compiler allows that. Otherwise, you get a compilation error. And obviously, you can go and force it by explicit casting, but then here let's just not do that. And we said that we cannot use underscore between 0b, which is a declaration that we're defining a binary. And we can use anywhere else, right? So these are the bits. 0b is not part of the number, so we cannot use basically underscore between b and the 0. So we're defining a bit, and then let's do a sysout byte to basically integer. We're going to use the integer to a string, to binary a string, and then b1. Remember, this is a utility class in the integer that returns the bit pattern as a and it gives me 0001. It disregards all the extra zeros, right? And then we can also do a sysout on the b1, and this actually prints the decimal value, right? Remember that this one calls the overloaded print line that takes a integer. And why is this? Why is there no basically overload for byte? Because a byte can be safely converted to int, so they decided not to go with this. If I open up this print line, and so we have a print line that doesn't take any parameter, print line that takes boolean, print line that takes char, print line that takes int, and line. But there is no mention of print line for example, byte or short, because they can be safely converted to int. So they decided to go only with these. And the reason is that, again, memory doesn't really matter that much. If you have a byte and then convert it to int, eventually in the bytecode everything is an integer, 32 bits. So there's really doesn't matter if byte is converted to int or not, right? So there is no overload for the print line that takes a byte or short, because it just calls the one that takes an int. Byte and short can be safely converted or implicitly converted to int. There is no problem. Now byte b2 is not b1. So this is the unary bitwise not operator, and we are flipping the bits, right? Now the question is, why are we getting error? Because basically what happens here is that it says that type mismatch cannot convert from int to byte, right? So this one, when you use this, interestingly enough, it let's see if we go with 7 bits, it still complains. And that's it's very interesting that we're using 8 bits, and then when we try to do a not on it, it just says that it should be int, right? So we could in fact go with int. There is no harm in that, and I recommend that you try to always stick with int because memory doesn't really matter that much. And again, in the bytecode, we've seen before that eventually all the integers are treated as 32b, unless it's a long integer like 64-bit long. Then there's a special bytecode for dealing with that, because the stack in JVM is 32-bit. So let's also look at the bits here now. B2. What do we expect to see? Our expectation is that B2 becomes basically all the bits flip 1 1 1 1 and then 0 1 1 1, right? And this becomes from 2's complement, this becomes a negative number when converted to decimal base, right? To base decimal, base 10. So let's have a look at this. As you can see, remember that this is actually translated into 32-bit. So we have much more bits here, and everything is basically ones, right? And then what happens here is that we get a value of -9 or -9. So all the bits here are 1, right? And the way this works is in the 2's complement, basically you invert it, and 8 becomes -8, and then -1 becomes -9, right? So that's the way it works. So we have lots of bits because this is a 32-bit integer, and then we invert the bits, and then we get this. So B2, and we get -9. And So we have all these. So we get this, and then basically it becomes -9, right? So you invert all the bits and you get 8, and then you add 1, it becomes 9, and then the sign flips, becomes -9. If you're not familiar with the 2's complement system, you can I recommend you Google it and search for it to understand how this works. Now obviously almost all the time we deal with decimals, so this may not be that important for us, right? Now let's also look at the bytecodes to see what bytecode is used for this special operand, unary bitwise operation. So in test 1, we push a 8 to the stack. Remember, this is still an integer literal, so we are pushing 8 and store it in the index 0, which is a pointer to this variable b1, and then this static fill out, and then we have to, after we get a hold of this field, we have to evaluate this first, because this is a argument to the method of this object. And in order to do this, we have to first load b1, which is at the index 0, and it's an integer. I load 0. Invoke a static. We're invoking this static method to binary string, and then invoke virtual. This is print line is a virtual or non-static method of this out, which is a static field. And then again get a static. We get this out, and then we load b1, and then invoke virtual, which is print line. So all this up to line 17 here is just for executing these 3 lines of code, right? And after that, we load b1. Again, assignment is a binary operator. The right hand side must be evaluated first, and the return value of the right hand side is assigned to the left hand side. So we load b1, iconst m1. So this is the bytecode that is being used. Bytecode is iconst m1, and basically and then I XOR. So it's very interesting that what happens, we do iconst m1, and then I XOR, integer XOR, and then I store store an integer in the index 1 of the stack, which is a pointer to b2, right? It's a memory pointer to a Java heap memory location. Now what's going on here? What's happening? So this very simple operation seems to translate into 2 bytecodes, which is very interesting. Now iconst -1 or -1 is a very special bytecode for -1 integer. So the integer -1, it says it says that -1 iconst -1. So basically load an integer. This is very similar, for example, iconst 5 or something. So let's say if I put here int x equals 5, for example, and then save this, the bytecode is updated, and then I get iconst 5. So iconst is just a bytecode that says that load this literal. Const means it's a constant, it's a literal, right? And then so we are iconsting or loading a constant integer, which is -1, -1. So, and then what happens is I XOR. So XOR is a binary operator. So we are XORing 2 numbers. What are 2 numbers? So number 1 XOR, which is which has a symbol like this, num2. And what is the num1, num2? So remember, in the stack, when you have a bytecode, it looks at the last 2. It's a binary operator, so it looks at the last 2 positions on the JVM stack and then loads those values. One of them is -1, which is the second one. The other one is I load 0 b1. So the other one is the value of b1, which is an integer 8. So basically what we are doing, this not actually translates into a just XOR. So this iconst -1, it just says that, okay, load -1. And it's very interesting that even for loading -1, there is a special bytecode to just loads -1. which is a constant number. And then noting the b1 means XOR this value with -1. Now, what is the bit representation of number 1, -1? Let's look at this. So why is this -1 is important? So let's do a sysout of integer to binary string -1. Let's go back to the console and run this. It's actually this one. So -1 has a very special bit representation. So -1 or -1 has a very special bit representation, which means all the bits are 1, right? And then the way you calculate, obviously this is a negative number because the leftmost bit is 1, which means it should be a negative number. How do we calculate the actual value of the negative? Is we flip all the bits, it becomes 0, and then we add 1, it becomes 1, and because it's negative, its decimal value becomes -1, right? So you flip all the bits. So for a negative number in a 2's complement, you in order to get the value, you flip all the bits plus 1, add 1 to the number, and then add a negative sign, right? To get the decimal value. Decimal value is basically this. That's the way you work in 2's complement. And same with our, and then what's interesting is that the not, instead of going and flipping all the bits, it's an XOR. And I believe the reason is that CPUs don't have a intrinsic instruction for flipping the bits. CPUs can only do logical operations like AND or XOR. That's why flipping all the bits translates into a XOR. And why does this work? What is XOR? So the question is, how does XOR logical operation work? So XOR, it says that the truth table. So if I have so this is my variable 1, and then I want to XOR it with variable 2. And the way this works is that if this is 0 and the other one is 0, then the XOR becomes 0, right? And then if this is 1, variable 2 is 0, this becomes 1. And if this is 0, variable 2 is 1, the result of XOR. And remember, 1, when we say 1, these are bits, right? These are bits, not the actual number. It's a bit. One bit is 1, the other bit is 0, because XOR is a bitwise operation. And when we apply it to, for example, integers, it just means we're applying them bit by bit, because 2 integers are 32-bit, so we can XOR each bit, right? So these are bitwise operation, right? This becomes 1, and then 1, the other one is, and this still becomes 0. Now this is, if you recall, for the OR operation, bitwise OR, we saw that if the 2 are true, or in the bit terms means if the 2 are true or the 2 bits are 1, the result is 1. That's why this is called exclusive OR. Exclusive ORs means there is a mutual exclusivity here. If only one of them has to be true, or the bit should be 1, the result in 1. Otherwise, the result should be true. They cannot be true. They have to mutually exclude each other, right? That's the meaning of XOR. Now, if -1 is all bits 1, then if I get my 8, this is the value that I have in my binary, right? So let's see. And let's go here. Now let's see what happens. Now my original value is this one, and we know that it's 32-bit, so there are lots of zeros here, right? And so 4, 8, 16, and then I think I need one more here. 8, 16, and then 16. This is 32-bit, right? And then our -1, so this is our number, is an integer, 32-bit, its decimal value is 8, and then our -1, surprisingly, is all 1, right? That's the feature of 2's complement. All the bits are 1. And then what we do is that we bit by bit do a bitwise exclusive OR. And note that what happens whenever a bit is 0, -1, all the bits are 1. So whenever a bit is 0, then the result is going to be 0. So nothing changes up to here, right? But then whenever a bit is 1, because -1 is also 1, 1 becomes 0. And then no, actually, because whenever a bit is 0 and is XORed which with 1, you end up with actually 1. So so all the way to here the result is going to be 1. And then whenever a bit is 1, when you XOR it with 1, it becomes 0. Whenever a bit is 0, you XOR it with 1, you basically get 1. You see the net result is that if you XOR bit by bit to a number that has all the bits as 1, which is -1. So -1, a constant -1, an integer -1. In the 2's complement representation, all of its bits is -1. That's why there is a very special bytecode that just loads -1, which is very easy, interesting. And the reason is that this -1 comes up a lot. So if you have an operation not that can be translated into a bitwise operation for using XOR, then you want to also have this number that has all the bits 1 around somewhere, right? So you want to treat it especially because this can come up a lot. That's why in the bytecode not, in order to calculate the not operation, we first load the -1 with all the bits are 1 and then do a bitwise XOR operator, right? Now we can also obviously do this. Int b3 is b1 XOR. I believe this is the symbol with -1, and then do a sysout on b3. Now this should have exactly the same effect as yeah, so this has exactly the same effect. The bit representation is exactly the same as notting the number. So this is equivalent to not to bitwise not of b1. So you either get your number and XOR it manually with -1, or when you go to do the not in the bytecode, we actually just XOR it with -1, because CPUs have an intrinsic operation or a assembly code just for doing the XOR, and then they just XOR it with all the bits 1, and then it essentially flips all the bits, right? Now let's see what happens in the bytecode. So in the bytecode, if I manually do the, so where is test 1 here, and where do we load b1? So here, for this line of code, b1 XOR to -1, we load b1 because this is a binary operator XOR, and this is a bitwise XOR, and it has to always evaluate the left hand side first. So the b1 loads in the memory, and then iconst -1 is loaded in the memory, and then we do a XOR integer XOR, and then store them in b3. Now compare this. So this is the lines of code that we have for this operation, and compare it with where we actually loaded b1 and then did the not. These are pretty much exactly the same, right? This is the main thing that I want you to understand, right? The not operation in the bytecode, it translates into XORing b with -1, and the whole idea is that -1 has all the bits 1, and then if we XOR this with a number, essentially all the bits flip. That's because the way the XOR or exclusive OR works, right? All right. Again, it's always very nice or very instructive to look at the bytecode to see actually what happens to bytecode. That's one of the goals that I follow here. I show you the bytecode, and so that you understand what happens. Sometimes the way bytecode translates your source code is not exactly what you expected. All right, so there are other binary operators or bitwise, like shift left. It shifts all the bits left and shift right, and you have to be careful. We talked about the underflow and overflow that happens with the integers, so you have to be very careful about it. And this is a binary operator. On the left hand side you give it an integer, on the right hand side you give it how many bits you want to shift. If you have an integer, you shift it by one bit, you essentially multiply it by 2. So that's the fastest way to multiply an integer by a factor of 2. Public static void test2. And then let's say int I1 is 4 or 5, right? Sysout I1, int I2 is I1 shift left by 1 bit, and sysout I2, and I'm printing the decimal values after I do a bitwise shift test2. All right, let's have a look at this one, and we get 10, and we can continue this. So if I want to shift I1 by 2 bits, I essentially multiply by the power of 2, so powers of 2, as long as no overflow happens, for example. So I3 is, which means if I shift by 2 bits to the left, I'm saying that take I1 multiplied by 2 to the power of 2, which is 4, right? Sysout I3. And this gives me 20 because 5 times 4. And if one more example, let's shift by 3 bits. This means 2 to the power of 3, or 8. 8 times 5 should give me 40. Yes, and let's quickly see what happens in the bytecode for this kind of operations. Let's see if the JVM does something tricky or not. So in the bytecode, for the first line, we load the constant 5, store it into the I1, we print it, and then in order to evaluate this, first we load I1, so from this line, and then iconst 1, the right hand side, I shift left. So there is a special bytecode for this operation which is called integer shift left. So integer shift left, and then this translates directly to how your CPU handles this kind of shift left, and then I store 1. So this is only one operation, and I'm guessing that this has an intrinsic translation into JVM, so it directly uses an assembly instruction that your CPU supports. Same for here. So this was shifting 1 bit. What about so I shift left is a binary operator, takes the last 2 values on the stack. So for example, for this one, the bytecode is still I shift left, but its operands is I1 and the integer 2. Then it knows how to shift by 2 bits. So these are all the same bytecodes, but then this bytecode requires operands, so 2 operands. So it knows how to shift by how many bits, right? Now obviously if we shift a lot, let's say 300 bits, this works, but let's say integer is 32 bit, right? So let's say we shift by 30 bits. We're still not getting overflow, so 31 bit, let's run it. Now it becomes negative, right? 31 bit, if the first, so 5 is, let's set it to 1, so the rightmost bit is 1. So 31 bit is still overflow. 30 bit is okay. Because we're still positive, but then if we go 31 bit, it's going to give us a negative number, right? And then 32 bit, it gives us 1. So every 32 bit you circularly go back. So one key thing that notice here is that it's the shift left, or shift left is circular, which means after 32 bit all the bits don't become 0, it circulates back. So if I say 33 bits, then it multiplies the original value, which is 1, by 2. If this was originally 5, I get 10. So you either shift by 1 bit or 33 bit because it's a circular operators, right? Remember that these are circular. So the signed left shift operator shifts a bit pattern to left, and the signed right shift operator shifts the bit pattern to right. The bit pattern is given by the left hand operand, and the number of positions to shift by the right hand operand. The unsigned right shift, remember there is only one unsigned shift, which is shift to right, shifts a 0 into the leftmost position, while the leftmost position after this depends on the sign extension. So be careful about the unsigned shift. The bitwise AND operator performs a bitwise AND, and again it's similar to XOR. So bitwise operation means based on the type of your integer, it determines how many bits it has in the memory, and then you do a bit by bit logical operations. If you are not familiar with the logical bitwise operators or operations like AND, bitwise OR, it's very similar to the Boolean operations, true and false, but it's just bits. 0 means a false, 1 means true. And we said that, for example, for logical AND, only when the two are true, then the result is true, otherwise it's false. Same with bitwise AND. Only when the two bits are 1, the result of the bitwise AND is 1, otherwise the result is 0. So it's very similar, but these are operating on bits. The bitwise XOR and the bitwise AND. So this is a typo here. This has to be a single pipe, which means bitwise OR operation. So bitwise AND, the symbol is ampersand. Bitwise OR is a single pipe, a single line. The following program bit demo uses the bitwise AND operator to print number 2, right? So F, this is 15, and then we AND this, and then only you can figure out what is the value here. So this was the full discussion on the operators in Java. I hope you enjoyed this. Please stay tuned, and I'll see you in the next one.